Hello, my name is Jesse Wales, and I'm a PhD candidate in the Operations Research with Engineering program here at the Colorado School of Mines. Today, I'm going to talk to you about my research, which entails decomposing a renewable energy system design and operation optimization model. Let's imagine that you are the owner of the building pictured here, and you want to incorporate renewable energy and storage technologies to reduce your long-term costs or to add the ability to maintain some operations during a power outage, which is called resiliency. To help you make those decisions, you might want to turn to the National Renewable Energy Laboratories tool called REOPT Lite. During this presentation, I'm going to give an overview of what REOPT Lite does and describe what the model is. Finally, I want to describe a decomposition that we're going to do to greatly improve the solve times. REOPT Lite is a web application of the National Renewable Energy Laboratories larger model, which is called REOPT, that uses an underlying optimization model that determines the best mix of renewable energy technologies and battery storage in order to reduce long-term electricity costs and improve resilience to power outages. So imagine you're on this web tool. As a user, you're going to choose first whether or not you want to optimize your financial outlook for the long term, or you're looking for resiliency for your system. Next, you're going to put in your specific location, building size, utility information that you have. If you have a load profile, or if you're going to use a default load profile based on the size and type of building that you're going to use, and then which technologies that you want to consider to add to your system. Not pictured here is combined heat and power, which is a new technology that we're working with NREL to add to the REOPT Lite capabilities. So you make these selections, and REOPT Lite will help you optimize the best size and mix of these technologies. And in doing so, they're going to optimize the dispatch to meet your load profile. So here's an example output of the results. So this dark black line here is the site electric load for your building, how much energy that you're consuming on an hour-by-hour basis. In orange is how much electricity you're purchasing from the grid. In yellow is the photovoltaic generation, how much energy you're getting from the sun. And in this model, we have a battery. So here you can see the state of charge of the battery as it's charging. And as it discharges, you can see that you're creating energy with that battery to help either shave off the peak and save money, or maybe get you through a resiliency period. A REOPT is an intricate model that has a lot of inputs to it. And the underlying engine is a mixed integer linear program. So this mixed integer linear program optimization model is trying to either reduce long-term electricity costs or improve resiliency of your system. It's going to optimize decisions or of what technologies to use, the size of those technologies, for example, how big of a storage system you might need for your building. The inputs of that model we talked about a little bit already, and there's a lot of constraints that go into the model. Just listing a few here are the electrical and thermal demands of your building, load balancing, different pricing tiers, both in purchasing electricity from the grid and if you have the ability to sell electricity to the grid, and production incentive limits, such as using certain sizes of photovoltaic cells. So this model is used to help users make decisions with a web-based tool. And as a web-based kind of real-time tool, the users are expecting answers quickly, and they may be discouraged if they have to wait a long time. For example, a small case of this model with wind only and no pricing tiers solves in about 4 seconds. So that's really fast what we're looking for. But a larger case that's including a lot of different options, photovoltaics and battery, different pricing and demand tiers can take over 10 minutes to solve. That's a long time for a user sitting at a computer to wait for an answer, especially if they want to try a couple of different settings and options. That's a lot of time to do that. So we're really trying to improve these solve times. These solve times are also going to get worse when we add the combined heat and power that I was talking about. This combined heat and power introduces a lot of nonlinearities, which there's ways around those, but that could also increase the solve times. So therefore, we're introducing a decomposition to improve the solve time. So before I get into the decomposition, let's introduce some variables. So let's call variable X. That's just going to be a design or an overarching variable. So for example, a technology system size. So if we look at our graph from before, maybe the maximum amount of energy you can get from your photovoltaic panels would be the system size of your PV system. Next, we could look at Y, which is our operational variables. So this would be the technology power produced in a time step. So for example, how much energy in hour 12 that you're getting from your PV panels, or overnight, maybe in a certain hour, how much energy you're getting from the grid that you're buying. So these are an hour by hour, usually, type of operational variable. And finally, in order to aid this decomposition, we're introducing a reset variable, or a block reset variable, as we're calling it, R. And so in this example, at the end of the week, you have to have some certain state of charge R, maybe 0, but probably not going to be 0, in week to week or month to month. And this allows us to connect all the blocks in the end. So how does the decomposition work? So we take this original problem, which is meant to be a solution for an example year for your building, and we're going to break it up into blocks. So let's just say, for example, months. So we're going to break it up into months. We're going to call these months L in set L, and connect the blocks with the beginning and end of block reset variables. We're going to let X superscript L and R to the L be the block values of those design variables or those reset variables. So as we break it apart, each block, or each month in this case, can have a different design. You can have different technologies involved, different sizes of those technologies, and then we're going to reformulate our objective, summing over all those blocks. And we're going to penalize any difference in technology sizes, for example, between block to block. So how does that work? So we can take that broken up problem and create a lower bound, solving all these different months in parallel and penalizing differences between those blocks. So how do the penalties work? We can use penalties mu and theta here for each block. And anytime that block has a different design than the overall design of the system, or the average design of the system, then it incurs a penalty. Now, this is a relaxation to our whole problem. And as a lower bound, it's an infeasible solution. It's not a realistic problem, but as the name implies, the lower bound solution is the lower bound, or the best that you can possibly do, because we've actually removed some of our constraints. Now, the upper bound problem, we take the overall variable values and fix them for each block. So for example, the design in month 1 and January and February and March, all those designs have to be the same. And so we're going to get that information from the data that we have from those lower bound solutions. We can resolve all of these in parallel to give us an upper bound. So the upper bound provides a true feasible solution, though it may not be a good one. As its name implies, the upper bound solution is the upper bound on costs, for example. And you can do no worse than this because you have this real implementable solution. Now we're going to iterate between the lower bound and upper bound until that gap is reasonable, something that we can accept. And they're both going to converge on the optimal solution. To show it another way, we start with this original problem, and our time frame is the entire year. We don't have really any reset variables except for maybe the end of the year. And you can process out a lot of the solution in using linear programming techniques, but you're solving it all at once. But what we're going to do is we're going to break it into a lower bound problem where every block, for example, month, can have its own design and its own reset variable. And we penalize those differences. Then we take one of those solutions. So for example, we're taking the solution here for the first block, and we implement it across all the blocks, and we use the exact same reset variable. Now, each of these problems can be put out in parallel and solved quickly, and we converge back and forth until we end up with a solution to our original problem much faster than we had gotten before. So where are we? For the larger case, the block subproblems are solving in about 10 seconds. When we solve them in sequence, we're expecting to get improvements when we put those in parallel. The next steps are to do that parallelization, to write the script, to iterate between the lower and upper bounds and updating those penalties. And then finally, we're going to add combined heat and power technologies, as we talked about before. I want to thank the efforts from NREL and their funding and supporting this project. Thank you.